So in the previous video, we've talked about how the EMF is induced, and the EMF, as per Faraday's law, is basically proportional to the rate of change of magnetic flux linkage. But then in one experiment that we were doing initially, we also saw that the galvanometer needle was deflecting in opposite directions depending on whether the magnet was being moved into or out of the coil. So this is the diagram that I'm talking about, and we already looked at that. Now if you think about this, when this magnet is being moved towards the coil, so we talked about how an EMF would be induced, and that would be basically due to a rate of change of magnetic flux linkage. So the coil would be cutting these lines of flux leading to an EMF, which would be translated to a reading on the galvanometer. So we also know that when there is a current which is going to be flowing into this part, it will also create a magnetic field of its own then. And this is basically because of Fleming's left hand rule, what we talked about. So all currents also have a magnetic field around them. Now if you think about this, and let's say we are talking about when this bar magnet is being moved towards the coil, if I say that this pole here was north, and let's for the sake of argument say that the pole which was here was a south pole, right? Let's see what happens now. So if this was a south pole, then what it would do to the north pole is, even if we just push it slightly and the current is induced, so the south pole would keep attracting the north pole towards itself, and it would keep pulling in the bar magnet. So the rate of magnetic flux linkage would keep increasing, leading to an increased EMF and hence an increased current. But we know that that is not what happens when we do this practically. So instead what we end up concluding is that this pole must be a north pole. And even if you think about this, if I just take time back and talk about the south pole, so this actually goes against what we know to be true in physics. If you think about this, so I only gave a small push. So I gave it some, I applied some force, I did some work on it. Basically I gave it some kinetic energy. And that small amount of kinetic energy is basically, if this were a south pole, this would be giving me an infinite amount of electrical energy. So this is basically creation of electrical energy from nowhere. And we know this cannot happen. So what must then happen is that this pole must actually be a north pole. So the current would flow here in such a way that it creates a north pole here, and then obviously the other one would be a south. So what would happen is that if we were to move this inwards, and let's get rid of this for now. So everybody is clear on that I'm talking about the magnet moving towards the field. So then this must be a north pole here. And if you think about this, then what would happen is when I apply some force, I give it some kinetic energy. So I am providing some kinetic energy, and that leads to some electrical energy in the circuit, basically because of Faraday's law. So you know that if I push this slightly and if I bring this to a stop, then the galvanometer reading again comes to 0, right? So then there is no EMF induced. So then to again have a reading, what I must do is I must apply some force and do some work on the bar magnet, give it some kinetic energy so that it moves, and then that is basically converted into electrical energy. If you have a setup like this, and what you would find in that when you do such an experiment is also that you actually feel that force of repulsion. It is harder to push the magnet towards the coil because of the force of repulsion that is felt. So then this must be a north pole to basically oppose this movement of the magnet into the coil. And now that if we know this is a north pole, we can use the right hand grip rule for a coil to figure out the direction of the current. So my thumb should point in the direction of the north pole, and then when I curl my fingers, I'll find that the current is going in a direction like this. Right, so this is how current flows through this circuit. So this is what Lenz's law is about basically. Let's also talk about the second scenario if the magnet was being moved away from the coil. So if the same magnet is now being moved away from the coil, what we know would happen is that the galvanometer deflects in the opposite direction. right? So this is opposite to what it was previously. So again, by the same argument, what this means is that this current would also flow as to oppose the changes that cause it. And this is what Lenz's law actually is. When I write it out in a while, you'll see. So then this pole, to oppose this magnet going away, it would basically want to stop it from going away. So then it produces a south pole here, and then the other one must be the north pole accordingly. And now again, when I use the right hand grip rule, in this case I would see that the current flows like this through the coil, then downwards, causing a deflection like this. So now let's go ahead and write the official statement for Lenz's law. So Lenz's law so this basically says that the direction of the induced EMF is such as to create effects to oppose the change which produced it. So as we saw above, when the magnet was basically being moved inwards towards the coil, so basically it wants to oppose the motion of the magnet into the coil. So to oppose this motion, it must produce a repulsive force, which is possible if you have the same pole which is here at this position. So then this is basically producing effects to oppose that, right? So the induced EMF creates effects. In that case, the effect is basically the direction of the current, which creates a pole like that, and that is going to oppose the change, which was basically the motion of magnet into the coil, since in the first place it was the motion of the magnet that gave rise to the EMF. And you have the same idea here as well, that if this is going away, and this causes a reading on the galvanometer here. So basically to avoid, to oppose this motion of the magnet away from the coil, it wants to attract it, and that is possible if you have a opposite pole to what is there here. So it produces a south pole, and again the south pole is produced by the direction of the current. So again the EMF produced such a current which creates an effect, basically an effect of attraction here, to stop the magnet going away. So this is basically what Lenz's law is about. Let's also write the idea about the conservation of energy we were just talking about. So what we just talked about was that the loss of kinetic energy of the magnet, because in both cases the force, the magnetic force is such that it is going to oppose however it's moving. So the loss of the kinetic energy of the magnet is converted to electrical energy in the coil. So basically work needs to be done to move the magnet continuously. So basically if we put both of these laws together, then what Faraday's law used to say was that the induced EMF was delta n phi over delta t. And Lenz came along and said that all is well here, you only forgot to put in a negative sign here, which basically shows that however the magnetic flux linkage is changing, the EMF will be in an opposite direction to it. So in terms of graphs, what this means is this. So if the graph for phi, the magnetic flux versus time is maybe like this. Right, so this is how the flux is changing with time. So we also know that usually whenever we'll be referring to this in our exam, the number of turns will be constant. So further we can also say that this equation can be written like this: minus n delta phi over delta t, and phi we know is BA. So we can also write this as minus n BA over T. Also, most of the times area is also not changing, it's really B which is changing in questions in our syllabus. So if the graph for delta phi looks like this, also another important thing here, that since phi is basically equal to BA, let me write it here, since phi equals to BA, so again, like what I just said, the area does not change. So I can say that phi is basically proportional to B for fixed area. So what this implies in terms of graphs is that the shape of a magnetic flux density versus time graph is going to be the same as the shape of a flux versus time graph, right? So they're going to have the same shape. Obviously the actual values would be different because it's being multiplied by A, but the shape would be the same. So using this idea, and let me write it here on the corner, that the induced EMF is minus n delta phi over delta t. So basically the relationship between both of these graphs is this, that the EMF time graph is the negative gradient of the phi time graph, right? So how you get the graph of EMF versus time is if you take the negative gradient of how the flux versus time graph is. So in this case, for example, we can see that the gradient here is some positive constant, but when I'm making this graph of, what was it? Yeah, so EMF versus time. So when I take the gradient here, so since this is some positive value with the negative sign, this means that approximately this would be some negative value like this. Then it becomes horizontal. So as you can see, the phi is not changing, and by the equations that we just saw, since phi is not changing, then E will not be there, right? Because the EMF is equal to the rate of magnetic flux linkage. So if the flux is not changing here, then no EMF will also be induced. So at this point, the EMF will actually be 0 like this. Then this is a negative gradient section. So this is some positive, this is some negative gradient, but when I apply the negative sign again, this would mean a positive value. So this is going to be somewhat like this. Obviously, let's keep joining the graph shapes as we go further. So because this is getting a bit out of scale, let's actually adjust this. Then again, during this section, the flux is not changing. So if flux is not changing, again, you will have no EMF induced in that part. So it's going to go like this. And again, it goes down, so a negative gradient. So this will again be some positive constant value. And as you can see, basically, what I've tried to do here is, since this part was not as steep as this part, this had a higher induced EMF as compared to this one. So this is how you get that entire graph. right? So this is the graph of EMF versus time. So usually whenever you have to sketch this in your exam, the examiner is quite flexible on the negative part, and this is basically only because you know that in EMF, whenever we talk about voltage, so the positive negative of the voltage, so which end is the positive one, which end is the negative one, is really of not that much interest to us, so we let this slide. But the idea of gradients is very, very important here whenever talking about these graphs. So make sure you have all the gradients cases basically for curves or lines. So make sure you're familiar with all of those.